A NASA probe has recently reached the atmosphere of the Sun itself. You heard us right, the Sun. The bright red ball that greets you with light every morning has aroused scientific curiosity since the very beginning of astronomy as an academic field. Well, you may be shocked to learn about a special NASA project in that regard, a project that can finally allow us to learn more about the Sun than ever before. Before we begin though, please subscribe to Futurephile to watch more fascinating videos on futuristic tech. Why is the Sun's outer atmosphere millions of degrees hotter, in Fahrenheit or Celsius, than the surface, which is only around 10,000 degrees Fahrenheit, 5,500 degrees Celsius? Small magnetic waves flowing back and forth between the Sun's surface and outer atmosphere, according to one theory, cause this dramatic heating. According to a new study based on previous NASA mission, the key is found in an area of the Sun known as the zone of preferential heating. Whatever the physics is behind this superheating, it's a puzzle that has been staring us in the eye for 500 years, Justin Casper, a University of Michigan professor of climate and space sciences, said. Superheating looks to be a strange process, based on what scientists have learned so far. Some chemical elements reach varying temperatures, and some heavy ions, or charged particles, reach temperatures far greater than the center of the Sun. As a result of all this heating, the solar atmosphere, also known as the corona, balloons above the Sun's surface. This atmosphere is observable during total solar eclipses when the moon passes in front of the Sun. During those occasions, the corona appears brilliantly in the sky for a few seconds. The superheating zone also contains Alfvén waves, which are small magnetic waves in the electrically conducting fluid, such as plasma, inside a magnetic field. The solar wind, a continuous stream of charged particles emerging from the Sun, flows quickly enough to escape the waves at the boundary of this superheating zone. However, below that, due to waves pounding the particles from all directions, the solar wind particles accelerate. But what's the question? What scientists really want to know is how high beyond the Sun's surface this heating spreads, and they use decades of solar wind measurements from NASA's wind satellite, which debuted in 1994 and is still operational, to find out. The scientists were particularly interested in measurements of helium, a prevalent element in the Sun. The temperature of helium was measured at various heights above the Sun by scientists. As ions in the solar wind hit one another, the rate of temperature rise in that element slows. The superheating zone terminates between 10 and 50 solar radii above the Sun's surface, according to scientists. However, further investigation revealed that the outer edge may be linked to the Alfvén point, the distance above the surface at which solar wind particles leave the Sun. According to a previous study, the Alfvén point can rise and decrease as the Sun becomes more or less active. As a result, Casper and his co-author looked at wind statistics year after year. Despite being wholly distinct computations, the outer limit for the superheating zone and the Alfvén point moved in lockstep in a very predicted way, Casper added. Let's take a look at the spacecraft itself, knowing what its set objective is. Well, it's a spacecraft designed to take photos and measurements in absolute layman's terms. A solar shield protects the spacecraft systems from the Sun's tremendous heat and radiation. The solar shield is hexagonal in shape, positioned on the spacecraft's sun-facing side, and is 2.3 meters, 7 feet by 7 inches in diameter, and 11.4 centimeters, 4.5 inches thick. It is built of reinforced carbon composite and is designed to endure temperatures of roughly 1,370 degrees Celsius, 2,500 degrees Fahrenheit outside the spacecraft. Absorption is reduced by a white reflecting alumina surface layer. The spacecraft systems and scientific instruments are positioned in the shield's shadow's core part, where direct solar radiation is completely protected. The probe would be destroyed and rendered inoperable in tens of seconds if the shield between the spacecraft and the Sun was not present. The Parker Solar Probe has to operate independently and quickly to safeguard itself, because radio communication with Earth will take roughly 8 minutes in each way. 4 light sensors were installed to be used to detect the first signs of direct sunlight coming from the shield limits, and reaction wheels will be used to relocate the spacecraft back into the darkness. The team describes it as the most autonomous spacecraft that has ever flown, according to project scientist Nikki Fox. The spacecraft's principal source of electricity is a twin system of solar panels, photovoltaic arrays, and these solar panels and equipment in this secondary array are kept at operational temperature using pumped fluid cooling. Now, What about the mission, you may ask? You'll be pleased to know that the probe was successful in reaching the sun and began conducting its mission. After plunging itself through the edge of the solar corona back in April, NASA's Parker Solar Probe effectively touched the sun, becoming the first spacecraft to ever come that close to our host star. On April 28, 2021, during its 8th flyby of the sun, Parker Solar Probe encountered the specific magnetic and particle conditions at 18.8 solar radii, around 8.1 million miles above the solar surface, that told scientists it had crossed the Alfvén critical surface for the first time and finally entered the solar atmosphere, wrote NASA on their official website page about the probe. Parker Solar Probe flew into and out of the corona many times throughout the flyby. This shows that the Alfvén critical surface is not formed like a smooth ball, as some had assumed, and instead, the surface is wrinkled by spikes and troughs. Scientists will be able to learn more about how events on the sun influence the atmosphere and solar wind if they can figure out where these protrusions match up with solar activity coming from the surface. As the Parker Solar Probe approached 15 solar radii, about 6.5 million miles from the sun's surface, it passed through a structure in the corona known as a pseudo-streamer. Massive structures that rise above the sun's surface and may be seen from Earth during solar eclipses are known as pseudo-streamers. It was like flying into the eye of a hurricane passing through the pseudo-streamer. The circumstances lowered in intensity within the pseudo-streamer, particles slowed, and the number of switchbacks decreased, a stark contrast to the bustling onslaught of particles the spacecraft ordinarily faces in the solar wind. For the first time, the spacecraft encountered an area where their magnetic fields were powerful enough to control particle movement. These characteristics proved the spacecraft had passed the Alfvén critical surface and entered the solar atmosphere, where magnetic forces control the movement of everything in the area. Parker will continue to spiral closer to the sun, ultimately reaching a distance of 8.86 solar radii, 3.83 million miles from the surface. The initial trip through the corona, which lasted only a few hours, is one of several planned for the mission. Parker Solar Probe obtained data on the genesis of zigzag-shaped structures in the solar wind, known as switchbacks, during previous solar encounters. The photosphere, which is visible on the sun's surface, is one place where switchbacks begin, according to the data. The solar wind is an unceasing headwind of particles and magnetic fields by the time it reaches Earth, 93 miles distant. The solar wind, on the other hand, is organized and uneven as it leaves the sun. The NASA European Space Agency mission, Ulysses, flew over the sun's poles in the mid-1990s and detected a number of strange, S-shaped bends in the magnetic field lines of the solar wind, which detoured charged particles on a zigzag course as they exited the sun. For decades, astronomers believed that these sporadic switchbacks were unique to the sun's polar regions. Parker detected switchbacks in the solar wind in the year 2019 at a distance of 34 solar radii from the sun. This piqued scientists' curiosity in the characteristics and prompted more inquiries. What were their origins? Were they created on the sun's surface, or were they fashioned by a mechanism that twisted magnetic fields in the solar atmosphere? The latest observations, published in the Astrophysical Journal, are the first to demonstrate that one of the genesis points is close to the solar surface. Parker orbited closer to the sun on its 6th flyby, less than 25 solar radii distant, providing indications. Switchbacks are found in patches and contain a larger amount of helium, which is thought to come from the photosphere, than other components, according to the data. When the scientists discovered the patches coincided with magnetic funnels that originate from the photosphere between convection cell formations called supergranules, the origins of the switchbacks were restricted even more. Parker's closer visits may yield more hints about switchbacks and other solar phenomena now that experts know what to look for. Scientists will be able to see into an area that is crucial for superheating the corona and propelling the solar wind to supersonic speeds, thanks to the data that will be released soon. Extreme space weather events, which may interrupt telecommunications and destroy satellites orbiting Earth, will require readings from the corona to comprehend and anticipate. It's really thrilling to see how our advanced technology succeed in bringing the Parker Solar Probe closer to the sun than we've ever gone, and to be able to return such incredible research, said Joseph Smith, Parker Program Executive at NASA headquarters. As the mission gets closer in the following years, we're excited to see what more it discovers. The Parker Solar Probe has been in space for over 3 years now. Its mission is to orbit the sun, drawing closer and closer to the star while sending back data from the array of sensors installed on board. Since it is going where no spacecraft has ever gone before, it will likely discover new secrets to explore and answer the questions yet left unanswered. Let us know what you think of this exceptional probe in the comments below. What other interesting and burning questions about the sun do you think could be answered? If you like this video, you may also enjoy this next video that is shown in the end screen. See you there!